Okay, so let's have a go at question 1. So we start off with finding the reaction at A. We have to define a few things here. So I'm going to define X to be going in this direction. I'll define my reaction to be going from left to right. And the law that we'll use for the majority of this question will be when you sum the forces in the x direction, we expect them to be 0. So let's apply that to A, to the external forces, which will include the reaction. So I've got RA, take away 50, go in opposite direction, plus 20 equals 0. So RA is going to be 30 kilonewtons. Part B. Calculate the internal forces and stresses, sections A, B, and BC. Now what we want to do here is make cuts. And it's best to go from right to left. The reason for that is because our RA was an unknown from the question, so I might have gone wrong here. So to avoid that, let's go from right to left. So the first internal force I come across will be this one here. You make your internal force always point towards the cut. So that's going to be the internal force FBC. And we, essentially speaking, just look at this section here. So we look whatever's inside this grey box, and we're going to apply this sum of the forces for that case. So that will give us minus FBC plus 20 equals 0. So that gives us FBC equals 20 kilonewtons. Okay, now let's do the same thing here, where our internal force will be FAB. And notice that my FBC's are cancelling out, or I don't have a cut. You can use either argument, valid. So we only have minus, let's go and do that in green, blue. So we only have minus FAB minus 50. I'm going to skip the FBC's, and plus 20 equals 0. So that becomes a minus 30, plus 30, and minus in the end. So minus 30 kilonewtons. So that's the internal forces done. Obviously the stress is straightforward. Stress equals force divided by area. So we want to apply that to these two terms. So stress BC is going to be 20,000 divided by BC's got 20 diameter, so pi divided by 4, 20 times 10 to the minus 3 squared equals, and this one here, I'll do the same. So the stress AB, let's keep this sign, might be useful, so that's in compression, 30,000 divided by pi over 4, and that's got 30 times 10 to the minus 3 squared. Let's work out these numbers. So the top one, 20,000 divided by pi over 4 times by 20 minus 3 squared, close the bracket, Press the Eng button. So we get 63.662 times 10 to the 6, or actually it's right there, megapascals. Okay, and now let's do the next one, minus 30,000. And that's 30. So minus 3, square it. So that would be minus 42.441 megapascals. Okie dokie. Right, so that's all of B done. Now for C, for the displacement. I want to refer to your formula sheet here, but displacement is going to be the sum of forces, internal forces, and the lengths of their particular sections divided by the Young's modulus of those particular sections and the cross-section area of those particular sections. So we've got F AB, length AB. Our Young's modulus is just a constant 200 megapascals, so I'll put that down as E. And area AB. Plus the next one, FBC, length BC divided by E, and that's ABC. So, actually, so if we notice a trick here, F over A is stress. So we could rewrite this as stress AB, length AB divided by E, plus stress BC times by LBC divided by E. So probably going to need a new page, but might be able to fit this all in one line. So we take our stress, AB, so that's this one here. I had it. Yeah, I still got it. So let's multiply that by its length, 250 millimeters, divided by 200 gigapascals. And the next one is the BC, so that's this one here. So that, notice I'm using the signs. So the AB section I'm expecting to get compressed a little bit, and the BC section I'm expecting to get extended a little bit. So plus 63.662 to the power 6 times by its length, 250 again, divided by 200 gigapascals. So overall, let's do this in millimeters. So overall we get 0.0265 millimeters. Okay, so parts D and E is looking like I'm going to need a new page. Quite a lot to do here. So let's go to a new page. Okay, you may have noticed a change of clothes, and I am going to have to update my solution on the internet because I made a mistake. So thanks to Will, he's pointed out that I misread the question. So look at the question here, and it says the rightmost load at sea is now replaced with fixed support. So this thing goes, and we just have a fixed support there. Okay, so I misread the question, so I'll update this. Brilliant. Right, so what do we want to do? Start off by using our formula. I need my calculator. So we're summing things in the x direction. We're going to have RC here and the RA there. So we have RA plus, or take away 50 plus RC equals 0. So RA plus RC equals 50. We are looking for the reactions. So the next thing to do is to make cuts through our beams here and find those internal forces. So this one here would be FBC. We're only looking at the forces in that grayed out section there when we sum the forces. So that's going to give me minus F, stick in blue, minus FBC plus RC equals 0. So FBC equals RC. Now let's do another cut, and it'll be coming here, so that's going to be FAB, FAB. They're both pointing at your cut, and you just imagine that you're just looking at all the forces you can see there. You can either say to yourself, well, the forces FBC are cancelling, or you could just say I don't have a cut there. Either argument's valid. So we've got minus FAB. Now we've got this force going right to left, and then we've got the RC force equals 0. So rearrange this, FAB equals RC take away 50. So we need another equation to solve this. So we're going to go back in effect to this equation here, and this time we're going to say, well, the point at C isn't moving. So we're going to use all of this again. Let's copy it. But this time we know that this location is the overall movement of that particular point is at 0. It hasn't moved. E and E are the same, so they can cancel. L, this section and this section are the same, so they can cancel. So we just end up with that F AB over area AB. Area is equal to pi divided by 4 diameter squared. So I'm going to get rid of my pi divided by 4s. So we've got diameter AB squared equals minus FBC D BC squared. Okay, so I can say that FAB equals minus FBC. Notice all our units are cancelling out here. DAB over DBC. Thanks for that. Don't know who that is. and then we're going to square that. Okay, so what we got, FAB equals minus FBC. The AB is the thick one, so that's the 30 millimeters, divided by the BC thin one, 20 millimeters, and we need to square it. So 3 divided by 2, square it, gives me 9/4. So minus FBC 9/4. So we've got equation 1, equation 2, equation 3, and we want to get rid of our f's. So the first thing I can do is get rid of FAB, easy enough. So equation 3 therefore becomes minus FBC 9/4 equals RC minus 50. So I want to make this kind of match equation 2. Actually, no, it's easier than that. Just substitute in RC to there. So we've got minus RC 9/4 equals RC minus 50. So what is that going to be? 50 can go on the left, so 50, and then I've got 1 take away 9/4. So minus 5/4. Oh, no. Why did I minus? It should be plus. (13/4). Yeah. Yeah, so RC's on the right. Yeah. Yada. That's all good. So therefore RC equals 50 times by 4 divided by 13. So that is 15.385 kilonewtons. No point comparing it to the previous case, it's quite different. So that's my RC value. And now let's go to equation 1. We want the reactions. So equation 1 therefore is going to give me RA equals 50 take away 15.385. So 50 take away previous answer gives me 34.615 kilonewtons. So these are kind of making sense. You've got the 50 get pushing it that way, and then you've got the two reactions sort of sharing a bit of the load going the opposite direction. So that's my RC, that's my RA, and that's D done. So all of that to find D. Calculate the internal forces and the stresses A, B, and BC. So we're just really going back to equation 2 and equation 3. So equation 2, FBC equals RC. And what does RC equal? 15.385. And that's kilonewtons. So let's find the stress for that. So 15,385, and the stress for the BC section, it's the thinner one. That's pi/4, and it's 20 millimeters times 10 to the minus 3. Square it. So 15,385 divided by pi divided by 4 times 20 minus 3 squared. So that's a stress of 48.972 megapascals. Let's do the next one. So this is E, and next one I'm doing is FA. Okay, so that's RC take away 50. So section AB I'm expecting to be in compression, so I'm expecting a negative answer here. So we've got 15.385 take away 50. Okay, times by 1,000 gives me minus 34,615 newtons. Okay, because I was in kilonewtons there, switching to newtons because I want to find the stress next. Force divided by area, minus 34,615 divided by pi over 4. This time we've got 30 times 10 to the minus 3 squared. So that number divided by pi 4 30 millimeters, square it, and surprise surprise, I get a negative answer, so same stress as before, but this time it's negative. So because we've got a symmetric problem, our stress is going one way or the other way, and it's being distributed evenly. 0, slight truncation error at the end. Right, so there we go. And hopefully that is now correct. I'm going to stitch those two bits of solutions together and reload it up to the big internet in the sky. Thank you, Will.